This is the mean value theorem. We say the mean value theorem for derivatives. There turns out there's another version, like a corollary to this theorem that we'll talk about in the second semester. But almost any time that anybody talks about the mean value theorem, this is the one they're talking about. If a function f is continuous over a closed interval a to b, and it's differentiable over the open interval a to b, then at some point in between a and b, call that point c, the derivative at c is equal to the average rate of change of f between a and b. So what this says, what's interesting about this, it says that somewhere on a closed interval of a function, if that function is continuous and differentiable, the slope, the actual slope of that function, the derivative, is equal to the average rate of change over that interval. So here's a picture to kind of help understand what's going on. If I have some function f, and I know f to be differentiable and continuous, I should say continuous and differentiable, and I have 2 points on that function whose output values I know, I could find the average rate of change over that interval by finding f of b minus f of a over b minus a. I could also call that the slope of the secant line. And it turns out the mean value theorem tells us that somewhere in between a and b, which are down here, there's a point c. And if I find the derivative at c, which means if I find the slope of the tangent line to f at c, then that tangent line is going to have the same slope as the secant line. That means the tangent line is going to be parallel to the secant line. Turns out this is critically important for proving that the whole second semester of calculus exists. And you're going to find that they have lots of ways to test it on the AP test. So we're going to do lots of examples. So a quick reminder, I'm hoping of some things you remember from geometry or maybe your algebra class. If we have an if-then statement, we call the part that comes after the if the hypothesis, the part that comes after the then the conclusion. So the mean value theorem has two hypotheses, two things that have to be true, two things that come after the if statement. The first one is f is continuous over the closed interval a to b. So when I say closed interval, I mean we've got the brackets on the ends there to say that a and b, f is also continuous at those endpoints. And there's a second hypothesis, which is f is differentiable over a b, the open interval a to b. It might be differentiable over the closed interval a to b, but it's not necessary for it to be differentiable at those endpoints. It has to be continuous at the endpoints and differentiable over the interval. And the conclusion part of the mean value theorem is the part that comes after the n, after the then. So the conclusion is, at some point c between a and b, this must be true. The derivative is equal to the average rate of change. So the slope of the function, the actual slope of the function, is equal to the average slope, or the instantaneous rate of change is equal to the average rate of change. So some things to notice before we try an example. We'll have some information that we need to use if we're going to employ the mean value theorem in order to prove the existence of some value. Sometimes we call that value c. Number one, we're going to need an interval of our function that we focus in on. So an a and a b, the a and the b that we use in the average rate of change calculation. We're going to need a function that's going to have to be continuous and differentiable on the interval that we're checking out. And a big difference between the intermediate value theorem and the mean value theorem. The intermediate value theorem we can use to prove the existence of a point on the f function if I apply it to the f function. The mean value theorem is used to prove the existence of a value on the derivative function, the f prime function, if I apply it to the f function. So that's this derivative. We're going to have to figure out what function we want to apply it to, which means what function, what derivative are we looking for a value on. All right, so here's a nice straightforward example to start with. I have a function f. I've been promised that it's differentiable. Twice differentiable means you can take the derivative and you can take the second derivative. So I know my function is differentiable. They haven't said where it's differentiable, so I can take that to mean it is differentiable everywhere. That's good because I'm going to need a differentiable function if I want to use the mean value theorem. And I know two ordered pairs. I know 2, 5. This needs to be the whiteboard. I know 2, 5 is on that function, and I know 5, 2 is on f. I've been asked to explain why there must be a value c in between 2 and 5 for which f prime of c is -1. So remember we said if we're going to apply the mean value theorem, we need a function, in this case f. We need to care about proving the existence of an output of f prime. So that's what I have here. I've been asked about the existence of -1 on the f prime function, and I have some information about f. They've been very helpful here. They won't ever mess with you. Here my a and b are going to be 2 and 5. This is the interval I'm going to be investigating. This is the a and b I'm going to use in the average rate of change calculation. So I'm just going to prove to myself, I want to find out if, well here, I'll say A is going to be 2, B is going to be 5, and I'm going to write f of b. I'm using f because this really is a function named f. You might have to change the function name in another problem that you're doing. F of 5 minus f of 2 over 5 minus 2. And I'm just going to simplify that. I'm really, really hoping that I get -1. If I don't get -1, something's gone wrong. Or I've picked the wrong A and B, but there's really only one choice here. F of 5, I've been told is 2. F of 2, I've been told is 5. 5 minus 2. So this is -3 over +3, which is in fact -1. So I'm going to be able to apply the mean value theorem using 2 as my A and 5 as my B. So I'm going to use the typing mechanism to write this up in words. All right, there's 2 parts to this answer. You could give them separately like I have, or you could incorporate it into one long line. So I'm going to show you what I did. I first computed the average rate of change over the interval A to B, and I got -1, which is the f prime value I was looking for. So once I have that calculation there on my paper, I can use the fact that that exists in my conclusion. So I said since f of x is continuous on the closed interval 2 to 5 and differentiable on the open interval 2 to 5, the mean value theorem guarantees that there exists c in between 2 and 5 for which f prime of c equals -1. One other option, if you feel like making it all go in one long line, you could have saved that calculation. You could have started your write-up here and gotten here, 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 all the way here. There exists c in between 2 and 5 for which f prime of c equals, and then here, instead of this just writing the number -1, you could have included this whole calculation, which arrives at the result of -1. So again, if I want to use this theorem, I have to be certain that my function, in this case my function f, was continuous and differentiable over the appropriate interval. So here, that was pretty easy. They told me my function was twice differentiable everywhere, and the function that's differentiable everywhere must be continuous everywhere. All right, so here's an application of the mean value theorem that has a little bit more work to do. I have a car traveling on a straight track. I know the car's velocity is continuous. I know its acceleration is continuous. And you may have seen a question like this in your free response notebook, and we have this question: is there a time, does there have to be a time at which the acceleration is 0? So if you were a chapter 2 student and you had the intermediate value theorem in your toolbox now, you would look at this problem and you would say, if I want to apply the intermediate value theorem to the acceleration function, I want to prove that there is a time when the acceleration is 0, I would look for an acceleration that is higher than 0 and an acceleration that is lower than 0, and then I could apply the mean value theorem. Well, I don't have that here. I don't have any acceleration values that are negative or even exactly 0 to use. So the intermediate value theorem here won't work. But it turns out we can apply the mean value theorem. The mean value theorem proves the existence of a value of the derivative function. So if I can recognize acceleration as the derivative of velocity, then I can apply the mean value theorem. I can try to apply the mean value theorem to the velocity function to prove the existence of an acceleration value of 0. So if I'm going to be able to do that, I could look here and see if they've maybe just handed me my a and b value. I could try to find f of b minus f of a over b minus a using time 10 and time, oh sorry, that was not correct. Time 0 and 60, but that doesn't, the average rate of change there is not 0. So I'm going to have to think about how I can choose. Is there any way I can choose my time values so that the average rate of change of my velocity is 0? Well, average rate of change is change in y over change in x. In this case, change in v over change in time. And that fraction is going to have a result of 0 anytime the numerator is equal to 0, which means I want my f of b, in this case, v of b minus v of a to be 0, which means I want my two velocity values to be equal. So I'm going to choose, I might only have one choice here. There's only one choice I see. So I'm going to choose those two ordered pairs on the v function. That's 0, negative 20 and 25, negative 20. And I'm going to compute the average rate of change. I'm expecting it's going to be 0. I tried to hand pick those so that I would get 0. Let's just prove that I got it right. I'm going to practice making sure I use the correct function name and all the correct notation when I perform this computation. So I'm going to call it v of 25 minus v of 0 over 25 minus 0. That is v of 25 is negative 20 minus negative 20 over 25 minus 0 is 25. And I do, in fact, have a numerator now of 0. So 0 over 25. So I found the average rate of change of the velocity function using a 0 and b 25. And I have an average rate of change of 0. And the mean value theorem I can then use to say that there must be a time t in between 0 and 25 at which the derivative of v, which is a of t, is equal to 0. So I'm going to write it up next. Notice I have my average rate of change computation, has to be there. It's my style to do it first, but like I said, you can write it up so it comes at the end of your statement too. And now I'll type in the words that I would write to justify my answer. So I had my average rate of change computation, v of 25 minus v of 0 over 25 minus 0, already set. And I started my write-up. The question is yes or no question, so I have to make sure I answer. So I said yes. Since v of t is continuous on the closed interval 0 to 25 and differentiable on the open interval 0 to 25, the mean value theorem guarantees that there exists a time t is between 0 and 25, for which v prime of t equals a of t equals 0. So now, this is the part, this is the part that the mean value theorem guarantees. that there's a time t between 0 and 25 at which v prime of t equals 0. It doesn't really answer their question because they asked a question about a of t. So it's your job to make sure that you make it clear to whoever's grading your test that you know that by finding v prime of, or by proving that v prime of t equals 0 at some point, you've also shown that a of t must equal 0 at some point. So I do that by just including that statement in here, closing that gap between v prime of t equals 0, which the MVT guarantees, and that question that they asked, which was about a of t. So I want to make sure I have a of t in my answer. But since I've applied the mean value theorem to the v function, that's why I know v prime of t equals 0. There must be a time t where that happens. So if you look in your free response notebook, typically there is one mean value theorem in the free response section, one mean value theorem question every year. And like I say in your notes, it's tested on the AP test the way that we've done these last two examples, not really the way that it's tested. It's, there's practice in your book. So focus on practicing in your free response book.